Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Ernest Orlando Lawrence's 1931 paper, co-authored with his student M. Stanley Livingston, titled The Production of High-Speed Light Ions Without the Use of High Voltages, represents a pivotal moment in the history of experimental physics. This document, published in Physical Review, encapsulates far more than a mere description of a new instrument. It articulates a revolutionary principle that fundamentally altered the trajectory of scientific inquiry into the atomic nucleus. The work's power resides in its elegant conceptual simplicity and the audacious scope of its vision, presented with a clarity and confidence that belied the immense technical challenges ahead. This essay will undertake a direct and systematic evaluation of the specific claims, theoretical underpinnings, and methodological arguments presented within this foundational text. By proceeding through the paper's logical structure, we can dissect the intellectual architecture of Lawrence's proposal, examining the soundness of each assertion and appreciating the intellectual leap it represented for a generation of physicists striving to unlock the atom's core. That analysis will illuminate how a succinct communication, built upon a single profound insight, could lay the complete groundwork for the age of the particle accelerator and redefine the scale of terrestrial physics. Section 1. The central principle of magnetic resonance. The paper commences by positing its core conceptual claim, the circumvention of high-voltage insulation difficulties through the repeated application of a relatively low potential. This assertion is the absolute foundation of the entire work. Lawrence and Livingston claim that ions can be accelerated to very high speeds through a cumulative process, a profound departure from the linear methods of his contemporaries, which required a single, massive potential difference. The evaluation of this claim hinges on the validity of the underlying physical principle of magnetic resonance. The authors propose a method where light ions are introduced near the center of a magnetic field and are made to spiral outwards. The brilliance of the claim lies in the isochronous nature of this motion. They derive and present the crucial relationship that the period of revolution for a charged particle in a uniform magnetic field is a function independent of the particle's velocity, or the radius its path. Expressed in language, the angular velocity of the ion is determined by the ratio of the magnetic field strength multiplied by the ion's charge to its mass. This specific claim, that the time for each half revolution remains constant as the particle gains energy and its spiral path widens, is the linchpin. An evaluation finds this claim to be theoretically unassailable within a classical, non-relativistic framework. It is a direct and beautiful consequence of equating the magnetic Lorentz force with the centripetal force. The genius here is its application, by recognizing that this constant period allows for synchronization with an oscillating electric field. Lorentz establishes the logical basis for the cyclotron. The paper's initial argument is therefore a powerful fusion of established electromagnetic theory with a novel and practical application, a claim whose soundness provides the momentum for all subsequent arguments in the Section 2. The design of the acceleration chamber following the establishment of the resonance principle. The paper details the proposed physical apparatus for its realization. The central claim here is that two hollow, semicircular electrodes, the Nophamus Ds, placed within a vacuum chamber and situated between the poles of a large electromagnet, can effectively implement the principle. The authors assert that an alternating potential of a few thousand volts applied to these Ds, synchronized with the ion's revolution period, will provide a small accelerating kick each time an ion crosses the diametrical gap. An evaluation of this section must focus on the practicality and sufficiency of the described design. The claim of functionality rests on several implicit assumptions. It assumes that a stable ion source can be placed at the center, that the ions will remain in a coherent beam within the median plane, and that the geometry of the electric field in the gap is sufficient for acceleration. The paper's description is spare, showing a confidence in the elemental nature of the solution. The claim's strength is its simplicity. The design avoids the cumbersome and dangerous cascading of high-voltage tubes seen in competing Cockcroft-Walton or Van de Graaff generators. The evaluation reveals a design that is, in essence, a clever resonant circuit for protons. Its feasibility in 1931 depended critically on the availability of powerful radio frequency oscillators and large, stable electromagnets. The claim that this specific geometric arrangement would work was, at the time of writing, a bold hypothesis whose proof rested entirely on the experimental results presented later in the paper. The brilliance of the claim is its translation of a physical principle into a tangible, and surprisingly compact, piece of laboratory Section 3 Mathematical Formalism and Energy Projections. The paper next presents the mathematical framework for calculating the final energy of the accelerated ions. The core claim of this section is quantitative. The final kinetic energy of an ion is directly proportional to the square of both the magnetic field strength and the radius of the chamber, and inversely proportional to the ion's mass-to-charge ratio. Specifically, the work provides the equation where the energy in electron volts is a function of these parameters. A critical evaluation of this claim confirms its mathematical correctness under the initial assumptions. This formula represents the machine's promise and its pathway to scalability. It makes an explicit, testable prediction. To achieve higher energies, one must build larger magnets. The claim's power lies in its prescriptive nature. It provides a clear blueprint for progress, suggesting that the ultimate energy limit is determined by engineering and finance, a starkly different outlook from the physical limits of dielectric breakdown that plagued high-voltage machines. The paper then uses this formula to make a stunningly ambitious projection. It claims that a device using a magnet with a 10,000 Gauss field and a radius of 10 centimeters could produce protons with energies of 1 million electron volts. This numerical assertion was the heart of the paper's persuasive appeal. It promised to deliver energies capable of inducing artificial nuclear disintegration, the holy grail of contemporary nuclear physics. Evaluating this claim from a 1931 perspective, it was an extraordinary prospectus. It transformed the cyclotron from an interesting piece of physics into a tool of immense potential power, directly challenging the supremacy of natural radioactive sources like polonium for nuclear research. The soundness of the mathematics gave this bold projection an aura of inevitable success. Section 4. The presentation of experimental evidence. The most critical section of the paper advances the claim that the theoretical principle and proposed apparatus have been experimentally validated. Lawrence and Livingston present evidence from a small, prototypical cyclotron. The central assertion is that they have successfully produced an ion current of 10 to the power of -9 amperes, corresponding to 80,000 electron-volt hydrogen molecular ions. This claim is supported by measurements of the ion current reaching a collector plate as a function of the magnetic field strength. The paper includes a graph showing a sharp peak in the collected current to a specific magnetic field value, which they argue corresponds precisely to the value predicted by the resonance equation for the applied radio frequency. An evaluation of this evidence reveals it to be both elegant and, for its time, compelling. The sharpness of the resonance peak is the key piece of data. It strongly suggests that the ions are indeed being accelerated in a synchronized, cumulative manner described, as any other stray effect would likely produce a broader, less defined response. The authors claim that the maximum energy was limited by the size of their modest laboratory magnet. They further assert that when the filament producing the ions was turned off, the high-speed ion current vanished, confirming the source of the particles. While a modern physicist might ask for more sophisticated diagnostics, such as a direct measurement of particle energy via deflection, the evidence presented was perfectly tailored to its purpose. It provided a clear, semi-quantitative verification of the resonance principle. The claim of producing 80,000-volt ions with a mere 2,000 volts on the Ds was a powerful proof of concept, transforming the cyclotron from a theoretical dream into a working reality. Section 5 Analysis of beam stability and focusing embedded within the description of the apparatus and its results is a subtle but crucial claim regarding the stability of the ion beam. The authors acknowledge that for the device to work, the ions must remain confined to a narrow region around the median plane of the chamber during their hundreds of revolutions. They propose that the shape of the electric field in the gap between the Ds provides a focusing action. The claim is that the curved electric field lines, bowing outwards from the gap, exert a component of force that pushes ions straying above or below the median plane back towards it. A critical evaluation of this claim reveals a moment of profound physical intuition, perhaps even serendipity. The initial analysis of this focusing effect was quite rudimentary. The authors understood that the field lines would be curved, and they correctly inferred a restoring force, what was less appreciated at the time, and what later, more sophisticated analyses by physicists like Robert Wilson would show, was the complexity of this electric focusing and its interplay with the magnetic field. The claim in the 1931 paper is essentially that the device possesses an inherent, self-correcting stability. This was a vital assertion, because without such a focusing mechanism, the ion beam would rapidly disperse and collide with the top or bottom of the Ds, precluding the accumulation of high energies. The initial success of the prototype, which worked without any special focusing electrodes, lent significant weight to this claim. It demonstrated that the basic geometry of the Ds fortuitously provided the necessary beam confinement, a happy accident of electrostatics that proved essential to the cyclotron's initial triumphs. Section 6 The vision for nuclear disintegration. The concluding paragraphs of the paper extend beyond the immediate results to claim a future role for the new device. Lawrence and Livingston explicitly state that their method holds the promise of producing protons with sufficient energy to disintegrate atomic nuclei. This claim positions their work directly within the most exciting and competitive field of contemporary physics. They reference the work of Gamow on alpha particle penetration of the nuclear barrier, implicitly arguing that their machine could create an artificial stream of projectiles to probe the nucleus in a controlled manner. An evaluation of this concluding claim reveals it as a masterpiece of scientific rhetoric and ambition. At the time of writing, they had achieved 80,000 electron volts, the goal of reaching the 1 million electron volt threshold necessary for disintegrating lithium, a key target, was still an order of magnitude away. Yet, the claim is made with unwavering confidence, grounded in the scalability argument presented earlier. The authors were effectively throwing down a gauntlet, declaring that the Berkeley laboratory now possessed the superior method for tackling the atom. This claim was a direct challenge to the high-voltage groups at the Cavendish Laboratory and the Department of Terrestrial Magnetism. It was a bold declaration of intent, transforming a report on a successful physics experiment into a manifesto for a new era of nuclear science. The historical irony, of course, is that Cockcroft and Walton would achieve artificial disintegration first, using a high-voltage accelerator, mere months after this paper's publication. However, the ultimate vindication of Lawrence's claim lies in the cyclotron's subsequent dominance as its energy capabilities rapidly surpassed all competitors, proving his vision for its potential to be entirely correct, if slightly In conclusion, the 1931 paper by Lawrence and Livingston stands as a document of extraordinary intellectual density and persuasive power. A thorough evaluation of its internal claims demonstrates a logical and compelling progression from a fundamental physical principle to a working experimental device and finally to a grand vision for the future of physics. The core assertion of magnetic resonance is theoretically impeccable within its classical domain. The proposed apparatus is an elegant and practical embodiment of this principle. The mathematical projections, while audacious, are soundly derived and provide a clear roadmap for advancement. The experimental evidence, though preliminary, offers a sharp and convincing verification of the resonance effect. The insightful, if incomplete, claims about beam focusing address a critical requirement for the machine's operation. Ultimately, The papers conclude in assertion of its potential for nuclear science defined the research program for a generation. The work's enduring significance comes from the complete and self-contained nature of its argument. It laid out a new paradigm for particle acceleration so thoroughly and persuasively that it immediately catalyzed a global effort to build upon its foundations, securing its place as one of the most consequential publications of the 20th century.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.